season. I am not a baseball fan. And obviously I'm not a golfing fan either. Did we have that conversation yesterday about golfing? Oh, that was sixth period. Yeah, I'm not a golfing fan either. I make fun of that a lot. It was because Dylan got called out to go to his golfing match yesterday. And when he left, I made some golfing jokes behind his back. But then he dialed into the class, and so I had to make some of those golfing jokes to his face. So let's just say I don't find golfing to be a particularly exciting activity. It's really hard for me to classify it as a sport, but I know it is, technically. So you guys are golfers, yeah. You want to make golfing exciting, though? I think you should put linebackers on the fairway. I think if you put linebackers on the fairway, golfing would be a lot more fun to watch. I would watch it every single time. If you had like when you went up to the ball, there was like a whistle blown and you had to get it hit and gone before the guy hit you. Oh, done. It'd even be better if you both had to start like the same distance away from the ball. I mean, at least you got a weapon. They just run at you with their shoulder and helmet and pads and stuff. So
that makes it more similar to hockey, though.
I'm okay with that. That'd be fine. I'd be willing to make it so that there's like a big hockey goal at the end and not just a little tiny hole at the end. That's fine. I think bear traps should be legal in the sand traps. I think if you stepped on a bear trap, it's a foul. You gotta do the whole thing with the bear trap now. So. No, I think anybody in the cart's cheating. I think they should have to walk it. In fact, more importantly, I think they should have to also carry drag a tire behind them as they make it across the course. Yeah, so anyways, I kind of find baseball to be the same way. It's a fun activity, but I'll classify baseball as a sport. But, it's a sport till about the seventh inning, and then I just want to go home. I've had as much fun as I can have. I've eaten as many hot dogs as I can have. It's just time. If the pitcher and the catcher and the batter could just kind of come to some agreement and let him hit the ball once in a while, I'd be happy with that. Stop bringing in the guy from the bullpen just to make him so we can't hit anymore. I want the game to be fun. I think if you hit the batter, he should be out. Could you imagine how much more fun it would be then? I mean, there it is. There's the game. I think the batter should be able to take the bat with him. They're going to make it a lot more fun. I think tackle should be okay in baseball. So, I mean, these are just things you could do to spice up the game a bit. So, okay, so physics. I want you to imagine this for just a minute. Have you guys heard of optimization? Calculus, guys, optimization? All right. You have done a little bit of optimization, not a lot, but you've done a little bit. Whenever you've been asked to kind of figure out the maximum or a minimum of a function, you've done a little optimization. So I want you to imagine this is the range equation. And if you're in baseball and you're in the outfield and you want to throw the ball to the infield, well, there is an optimum angle at which you throw the ball in order for the ball to make it, as far as possible on your throw. So if assuming your throwing speed has a maximum that you can sustain throughout a game and be accurate, and G's not going to change, what angle would be the most optimistic, the optimum angle in which to make the ball travel the farthest? Now, I think you guys have an answer to this, don't you? Even if it's just innate, what angle do you think it is? How do you think it's about 45 degrees? Okay, so let's show that if we have this relationship, it's not just a guess. It's got to be the facts, right? Many people don't understand that the sine function and the cosine function are percentages. People don't think of it like this, but in this class, we are almost always scaling a vector. We're trying to say how much of a vector is in that direction. We use sine and cosine to do so. In this case, in the case that we use it, sine and cosine are there. It's a percentage. It goes between 0 and 1, just like a percentage. So if we look at this function here, it's going to be optimum, maximized, when sine is at 1. So sine of 2 theta is only 1 when theta is 45 degrees. It's got to be the optimum angle. Here's the thing, though. If a baseball player throws the ball at 45 degrees, which I am sure they can do, the ball is going to have a path that we would expect any projectile to have. Something like that. But baseball doesn't do this. Baseball players are trained to throw the ball with a bounce so that they throw at a lower angle and the ball bounces. And the reason they do that, they claim, is that the ball gets to the target faster if you throw it with a bounce than if you don't. That's their claim. So if that's true, we should be able to prove it. Because I'm sure baseball players, beings of incredible physics skill, have done the math and can tell us how much faster the ball gets there on the bounce. So let's make some assumptions first. And I think these are not unreasonable assumptions. First, let's assume that the baseball player can throw the ball at the same speed, but at different angles. Does that seem reasonable? Yes or no? Okay, so there is the potential for them to throw it at V at an angle of 45 degrees, or they could throw it at V at angle theta, which we don't know what that is. Let's assume that when it bounces, it obeys conservation of momentum, which you may not know this, but you would if you played pool, that the angle of incidence will equal the angle of reflection, that it bounces off at the same angle. And that's true. You might not know that, but it should make sense. Whenever you've bounced a ball, that's what it's done. However, energy would not be conserved on the bounce. It would lose energy when it has contact with the ground. So let's say that when it does bounce off the ground, it bounces off at a reduced velocity, half the velocity. Loses energy. And maybe it doesn't, but I figure this is a conservative estimate. If all of this is true, and I see this all seems to make, how many of you would agree this makes reasonable sense? That you could throw the ball with a bounce and the angles would be the same, but the velocity would be reduced. We all okay with that? All right, good. What angle is this? What does theta equal? I want the number. And believe it or not, I think you can find the number. So that's my first question for you. Find out what theta equals. Now, I know you guys are like looking at me like I knew you'd be looking at me. Like, well, you didn't tell us enough, like how fast it's going or how far it goes. This is a comparison. So I think if you find the right comparison, you'll be able to solve for this angle. That it won't matter how fast they throw it, that if they throw it slower, the same ratios will exist and you'll still get the same angle. So it's not about the velocity. It's about the angle. So I'll give you a few minutes to think about it, and then I'm going to give you a hint. You guys at home, do you want breakout rooms? Because there's a lot of people there. All right, so I'm going to send you guys out to breakout rooms. They're going to be a little bit bigger because I think you need more people to help you kind of talk this out. So there we go. You guys here, I would talk this out. And just so you know, in fourth period and in sixth period, and this is for everybody in the room too, if you're looking for a place to start, consider that you have this as the range, which would be this formula if theta equals 45 degrees, right? You also have these two partial distances, this one, which I'll call R1, and this one, which I'll call R2. R has to equal R1 plus R2. You have an expression for R. Can you come up with an expression for R1 and R2 that has theta in it, that you might be able to put into these, where maybe some things will cancel out? Try that. Yeah, I'll come over in just a minute. Okay, guys? Give that a try. I got one more room to go in there, and I'll be right out.
Okay, I got 26.6 degrees.
You guys should listen to Victoria. She knows what she's doing. That's the right answer. I just jumped in on you right when you said the right answer. So I'm leaving now. So you guys heard that, right? It is 26.6. So if you got it, then you know what you're doing. So we'll give it about a minute, and then we will we'll go over it a bit. For those of you who were struggling, you have to start somewhere. And so I tried to give you a place to start, the range equation. So if you start with the range equation, what we do know is that at 45 degrees, V naught squared sine of 2 times 45 over G represents the whole distance the ball is going to travel. And I get it. Well, we don't know V, we don't know G, but that's okay. In a lot of these problems, start like this. You're making a comparison. So start. These variables that we're using are going to reappear like R1. R1 is going to be just that first hop that the ball does, which is going to be V naught squared still because it's the same velocity, but at a new angle, sine of 2 theta. But G is still the same thing pulling the ball down. So that's an expression for the first hop. And then the second hop, a little different though because V's smaller. It's cut in half. But the angle's the same. Help me out here. Be my friend. There. Well, the first thing I hope you notice is that it doesn't matter how fast you throw it. In all of these, if I throw it slower, I just get the same proportions. So I'm going to go through and cancel out the V naught squared. And I can only do that if I know V naught isn't 0, but I have it on good authority. If you throw the ball, it's going to have some velocity. And of course, I can cancel out all these G's too, which is going to leave me with sine of 2 times 45, which is 1, equals sine of 2 theta plus 1/4 sine of 2 theta. Well, everything just disappeared except for theta. And this is just 5/4 sine 2 theta. Now, I have to stop here, not because I want to, but because this affects a few of you. If I add 1 sine theta to 1/4 sine theta, I get 5/4 sine theta. Some of you are confused by that. I know because I've been dealing with this all day. So if you're still confused by it, it's because you don't remember your mathematics. So you could factor out the sine 2 theta, and if you did, it would be 1 plus 1/4 times the sine of 2 theta. That's where the 5/4 comes from, and that's for the person who was going to ask where'd the 5/4 come from, and I didn't want to answer that person. So I think we're kind of done with this problem, aren't we? Hopefully you see why, because that means that the whole thing was about figuring out how long it takes. That was the whole thing. So we found out what theta is, but what we'd like to know is it actually faster to do it this way? Is it? Now, herein lies the problem. We can't tell if it's faster or not. We don't know how long it's going to take because we don't know how hard we threw the ball. We could make up a number here, but in physics, we often make comparisons. So what I'd like you to do instead is, now that we know that the angle is 26.6 degrees and that will provide us with a good bounce that will allow the ball to make it to its destination, what we would rather find out now is, let's compare the time with a bounce to the time with no bounce. I want the ratio. By doing a ratio, I have the chance of variables canceling out just like I would with an equation. Because it's a ratio. And I know that if this ratio is less than 1, then the top suggests the bounce part is faster. And if this ratio is greater than 1, that suggests the bottom is smaller, so no bounce is faster. Let's figure out which is which. Now, I can't give too long for this, so you only get 5 minutes. So, because it's 3:25. And I want to be there when we have the aha moment. So I can only give you 5 minutes. If you want a hint, I will give one hint before you launch. And that is, time only showed up on this chart. I think we're back to the chart. The hard part is figuring out which of these two sides of the chart you should use. You can actually get the answer from either side, but you'll find that it's faster if you use this side. So, I'm gonna sneak away for a bit, let you guys bang it around for a while. Again, like I said, I think it's use the vertical side. I think it's faster. So I'll hit pause. The reason I suggested you use the vertical side and not the horizontal side might not be obvious to you. But remember, our goal is to figure out the time. If we use the vertical side, we get the advantage of knowing that delta y is 0. Which means we can get an expression for the time that doesn't involve how far the object went. Which is what we would have if we had to use this side. We'd be stuck with r. On this side, we're going to get something like 1/2 times g. I'll just put g in there. 1/2 times g t squared minus, v naught sine theta times t equals 0. I'm kind of squishing it in there because I'm going to need some space in a minute. So this is the expression we can use to figure out t. So if I work it out a little bit, I can factor out a t, we know that, and I'll be left with t equals 2 v naught sine theta over g. So let's see how this works. I'm going to go to another screen, write that over here, t equals 2 v naught sine theta over g. Put that to the side for just a minute and think about it for a minute. The bounce has t1 plus t2. Right, there's 2 times. There's 2 v naught sine 26.6 over g plus 2 v naught over 2 sine 26.6 over g. Divided by no bounce, which is going to be 2 v naught sine 45 over g. Now, hopefully you see that I can get rid of 2 v naught g in all of these. There we go. Lots of space. So sine 26.6 plus 1/2 sine 26.6, all divided by sine 45. All right, there you go. Whatever this fraction is, it tells us whether it's faster or slower. So that's just 3 sine 26.6 over 2 sine 45. Right? Because we get 3 halves. All right, I want the number. More than 1 takes too long to have the bounce. Less than 1 saves us some time. Gotta go, gotta go. We only got 1 minute before they're gonna ring that bell. Make sure your calculator is in degrees, clearly. I know you hate it when I say stuff like that. Don't look at me like that. Definitely Victoria's looking at me like that. So's Ernesto. Keeps giving me the side eye. All right, I figure 2 or 3 of you got to have it by now. So, it is less than 1. That's what we're seeing, right? So, what do we get? 0.9 what? Now, do you really think baseballers figured that out?
Yeah.
Is it worth it to save 5%?
Yeah.
It would be, yeah. It'll win you a pennant. You guys have watched these games before. Definitely. Definitely. All right. Sine of 2 theta equals 4/5. So that's where you fire up your fancy dandy calculator, you get that calculating machine out, and you tell me that it's 26.6 degrees. I mean, the inverse sine of 0.8 is actually 3 point something? But you have to divide it by 2 to get the right answer. So how are we feeling out there in TV land? You guys okay? How are we feeling in the classroom? All right, so